talk, we will see use of recently developed multivariate signal processing techniques in our laboratory and its applications for two problems related to brain signal classification. One is related to epileptic seizure detection, and second one is related to schizophrenia signals detection. So this is the overview of this talk. First, we will see motivation, and after that, empirical mode decomposition briefly it will be explained, and then we will see empirical wavelet transform, then multivariate empirical wavelet transform, then its application for detection of epileptic seizures from electroencephalogram EEG signals. Then iterative filtering will be explained, and its multivariate iterative filtering that is proposed by us, that will also be explained. And after that, we will see its application for detection of schizophrenia from EEG signals, and in the end, conclusion will be provided. So in real life, actually, we find many situations where there is a presence of multi-channel signals or multivariate signals. For example, if you see this vibration sensors, so here we can get multiple signals at a time. Similarly, during this EEG signal recording, we have multiple signals at a time, and electrocardiogram ECG signal recording from the various electrodes, we record many signals at a time. So there are actually there is a lot of interest in the literature to develop this multivariate signal processing technique, and this actually one of the reason that is acquiring multi-channel or multivariate signals these days is very easier due to recent progress in sensing technology. And due to that, actually, this a new topic of research, that is time frequency analysis of multivariate signals, is coming in the literature. And if you analyze multi-channel signal by considering all channels, then actually we can preserve the mutual information between the individual signals. And also this mode alignment property can be preserved. So if you don't use multi-channel processing, then actually this different channels will have different number of components or different number of functions, like intensity mode functions that we use for signal representation. So that we will see in the coming slides. So the recently actually this signal processing based on the empirical mode decomposition has been developed, and this technique is a little bit different, like compared to conventional techniques like in Fourier transform. We use sinusoidal basis function from our side. Wavelet transform, we use wavelet or mother wavelet from our side, but signal is not sinusoidal, signal is not wavelet. So actually we forcefully represent our given signal in terms of non-basis functions. And recently that actually this empirical mode decomposition method, it works in different ways. It is like, instead of using mathematical formula for performing transformation, we use an algorithm, and based on this algorithm, actually this we obtain the components or intensity mode functions from the signals. So this is actually a data dependent method, doesn't require design of basis functions, and also it doesn't require any condition about the stationarity or linearity of the data, and it has got actually a lot of a lot of attention in the literature. And if you see this very simple algorithm, we have signal, and then we determine maxima and minimas, and based on the maxima minima, we actually determine the two envelopes, and then we take average of both envelopes, and then we subtract from the signal. So that we call residual, and the residual should satisfy some certain conditions. They are actually these conditions show that whatever components or whatever IMFs, intensity mode functions, we derive from the signal, that actually represent the symmetric and sinusoidal kind of component, or these components are represented by AM, FM, amplitude and frequency modulated signals. So in that way, actually by using iterative algorithm, we determine all possible components or all possible IMFs from the signal. And here you can see one example. This is the signal that we want to analyze, and these are the obtained IMFs. So the first IMF represents the highest frequency component present in the signal, and the last IMF, for example, 8th IMF, represents the lowest frequency component present in the signal. And this first IMF is also corresponding to low scale of the data, and the 8th IMF is corresponding to the largest scale of the data. So this low scale also gives you the detail part of the signal, and large scale gives you the approximation part of the signal. So in that way, actually we can decompose any signal in adaptive manner using this empirical mode decomposition method. And based on this method, various approaches for multivariate signal representation has been developed, like complex empirical mode decomposition, rotation invariant, complex empirical mode decomposition, bivariate empirical mode decomposition, multivariate empirical mode decomposition, fast multivariate empirical mode decomposition. And these actually techniques have some limitations, this EMD based approach. So there is actually, there was development of the empirical wavelet transform. And we have actually extended that empirical wavelet transform into multivariate empirical wavelet transform. Then we have studied this for epileptic seizure detection using EEG signals. So human brain is actually highly complicated nonlinear system. And the electroencephalogram, which we call EEG signals, they measure the electrical activity which is generated by the neurons in the brain. And this is very serious disease and affects around 2% population of the world. And EEG signals are commonly used for the diagnosis of epilepsy. So we have proposed empirical wavelet transform based approach for patient specific epilepsy detection using surface EEG signals. And here you can see this is actually different parts of the brain, and corresponding electrical activities is actually recorded using this 10 to 20 electrode cap, that is electrode positions according to international 10 to 20 system. And this is actually, for example, a 2-channel EEG signal is shown, and in that way we can have multi-channel data. And what is the motivation for empirical wavelet transform? That is, EMD method actually suffers from two problems. One is actually it has mode mixing problem, and second one is it lacks mathematical theory. So due to that, actually, in order to overcome these limitations of the EMD method, this empirical wavelet transform was suggested. And empirical wavelet transform has actually 3 main steps. It determines the Fourier spectrum of the signal. Then we perform the segmentation of the Fourier spectrum, and based on the different segments, we design the wavelets, some other wavelets, and then based on the scaling function and wavelet functions, we actually separate the components. So in that way, that actually this is the just brief overview of the EWT method. So what we have done, we have extended this EWT method for multivariate signals, and then we have actually obtained time frequency representation of multivariate signals using EWT and with application to epileptic seizure detection. So if you what is the problem with the EWT method? If you apply EWT method for multi-channel data, then each channel will have different number of components. So what we have suggested, instead of using this spectrum of the each channel, let us go for the average spectrum of the all channels. So this is the multi-channel data YT, and this is actually average spectrum of the all channels spectrum. And based on that, actually we design the filter banks for each channel. So in that way, each channel will have same number of components, and there will be a mode alignment property will be preserved. And once you decompose this all channels using the same filter bank or same this Fourier spectrum, then we actually obtain the components, and then we determine the instantaneous amplitude, instantaneous frequency of the all components from the all channels. And then we determine this for each component joint instantaneous amplitude and joint instantaneous frequency by using this formula. And once it is done, then we determine multivariate time frequency coefficients for each oscillatory level by this mathematical expression. And finally, multivariate time frequency coefficient for all oscillatory modes can be computed by this formula. So in that way, we can have time frequency representation for multivariate EEG signal. And then actually we have also suggested use of 3 features from the based on joint instantaneous amplitude, which is mean of joint instantaneous amplitude, and this mathematical expression can be seen in the slide. And then mean monotonic absolute amplitude modulation change, which is mathematically expressed by this formula. And then variance of monotonic amplitude modulation change, which is expressed by the following formula. So these actually, these 3 parameters that is proposed by us, they are dependent on the instantaneous amplitude, because the seizures, they are more sensitive to the change in the amplitude. So due to that, we have actually proposed the features based on the amplitude parameter of the signal. And this is the proposed epileptic seizure detection system. So we have actually used Physionoid CGHP MIT scale P database, which has recording from 23 patients and 23 channels. And then this all channels, if used actually, then this sub method suffers from high computational complexity. So due to that reason, we have actually suggested criteria for the selection of the 5 channels. So that is channel selection criteria. So first channel with least standard deviation is selected, and after that other 4 channels are selected based on the relatively high mutual information with the first selected channel. So once you have 5 channels, then we apply empirical wavelet transform method, and they're based on the average spectrum of all channels. And then for each channel we have 10 modes, and after that for each channel from the all modes we compute instantaneous amplitude and frequency, and then we determine joint instantaneous amplitude and frequency of each mode, and then we whatever features you have seen in the previous slide, they have been extracted from the each mode. And after that we have suggested feature processing, and these processed features are given as input to machine learning based classifier, and then will automatically classify this data into seizure and seizure free classes. So this is actually one example. Here you can see 5-channel EEG signal, and this is for seizure case, and this is 5-channel EEG signal for seizure free case. And here you can see this time frequency representation based on the proposed multivariate approach that actually has frequency components in low and high frequency regions. On the other hand, if you see the time frequency domain of the seizure free EEG signal, which has only the frequency components in low frequency region. So this actually, this time frequency representation of the multi-channel data can be used as a feature set, or can be used as a signature to identify the seizure and seizure free patterns. And this is actually very useful for the such kind of algorithm can be used as in the form of software in the smartphone or computers or mobiles, and also can be used by the neurologists in their helping in their decision making process. So this actually, these are the proposed features, mean of joint instantaneous amplitude, and here you can see like before this filtering, there is a lot of actually variations. So this they are not showing a good discrimination between seizure and seizure free interval. Similarly, this can be seen for the mean monotonic absolute AM change and the variance of monotonic AM change. So what we have suggested use of moving average filter, which enhances actually the discrimination between seizure and seizure free part of these signals. And here you can see in the middle there is onset seizure, but when you perform filtering, there is onset is becoming clear in all the features. Then once you have filtered these features, then we suggested use of Hermite product, and which will actually multiply all these features together, and which will give you joint feature vector, which gives you the better separation between seizure and seizure free event. So that we will see from these results. So this is the EEG signal which has actually epileptic episode in the middle, but it is not clear for this surface EEG recording. It doesn't have good signal to noise ratio. But when you see the joint features, joint feature 1, joint feature 2, joint feature 3, and nice presence of the seizure onset. So that actually gives you very well localized seizure identification. And then these features are given as an input to machine learning classifier. And then actually we have compared our proposed system with other existing methods in the literature. So here from this table, you can see earlier people have used various signal processing machine learning techniques in order to identify these epileptic seizures using the surface EEG signals. And our proposed method has provided better identification and better specificity, sensitivity, and accuracy as compared to other existing methods which are studied on the same database. After that, actually, this empirical wavelet transform, that was actually one of the improvement of the empirical mode decomposition. Another improvement also in this empirical mode decomposition, that is done with the help of iterative filtering. So iterative filtering techniques subtracts out the selected part of the spectrum to extract the mode one by one iteratively. So like by maximum minima picking in empirical mode decomposition, we are doing actually separation of the components. And then actually that in empirical wavelet transform, these components are separated using filtering approach. That is by using this designing the filters based on the wavelet. Here actually there is another concept, and here also we perform the filtering using this iterative filtering concept. So the filter, this length, that it depends on the number of extremas. So by this mathematical expression, if you have high frequency components, the number of extrema will be more. So this L will be less. So this filter length will be less. So the cutoff frequency of the filter is inversely proportional to the length of the moving average filter. So that cutoff frequency will be higher. So that you will have actually like a high frequency component will be subtracted out from that. So this is the residual. So we signal minus this is the filtered signal, and then we have residual. And we repeat this so for so many iterations, and after that you have nice filtered signal, that is actually IMF. So we will see this one by example. Like this is the signal which has 3 frequency components. So the first iteration, and then we design the filter, that is a design filter, and then we subtract out this filtered signal from the signal. So then you will have high frequency component that we call first IMF. So second time, you will remove this second IMF from the signal. Sorry, this first IMF from this signal. Then this is the residual now signal residual, and from that again we design the filter, and from the design filter we subtract out this one, and remaining one is the second IMF. And after this first and second IMF, both will be subtracted from the signal, and then this you will have the I3, that is third IMF of the signal. So in that way, we can actually iteratively, one by one, we can determine all possible IMFs from the signal by using this iterative filtering concept. So this is actually flow chart of this iterative filtering for univariate case, and then we have extended this for multivariate case. So we have signal, then determine the maxima, minimas, and then we determine the filter length, and based on the filter length we design the filter, and then filtered signal will be subtracted from the signal, and then you have residual, and then actually you have to satisfy these two conditions. If this standard deviation is greater than threshold 0 and number of extremas greater than 3, this is a second condition, then we will repeat this process. So if any condition is not satisfied, then we will stop there. So in that way, we will actually determine all possible IMFs from the signal, and that actually we have extended for multi-channel data analysis. So multivariate EEG signal analysis. When you apply this framework directly, then each actually channel will have different maximum minimas. So you will have different number of components. So we have suggested this framework for multivariate iterative filtering. So this is a signal xn. Then we determine the number of maximas, and we determine the maximas for each channel, and this extremas, maximum minima. So extremas for each channel, and out of that we determine the maximum of this actually maximum minima or extremas. Then based on that we design the filter, and then we perform this filtering of all channels or individual channels by using the same filter. So in that way, number of components actually will be same, and then we satisfy these conditions, stopping criteria 1, stopping criteria 2, and in all cases actually we have multivariate IMFs, and then actually first multivariate IMF once you obtain, then you subtract from the signal, then determine residual, and then again you repeat the same process. So in that way we determine all possible multivariate IMFs from the signal. And this is the one example which actually demonstrates of multivariate iterative filtering concept. So the first actually case k equals to 1, this is the iteration 1, and here you can see the signal actually first channel has 2 IMF and the second channel has 1 IMF. So now we actually design the filter for first channel, second, and we determine the maximum of that. So this is actually filtered design filter. And based on this, we subtract from this, and then is the first IMF, 2-channel IMF, and then we subtract this 2-channel IMF from the signal, and this is actually residual. And then we design filter, then we subtract out from this residual, then we have second IMF, and then first IMF, second IMF, both are subtracted from the signal, this multi-channel signal, then we have third IMF. So all are multi-channel IMFs. And this is very nice example of this multivariate iterative filtering for real life signal. So like in ICU, actually we have this 2-channel ECG signal, electrocardiogram signal, and respiratory and seismocardiogram signal. And these signals, they have a lot of correlated information. So when you apply this multivariate iterative filtering method, then actually nicely you can have the different components from these all 4 signals. They have nice correlation and mode alignment property. And after this, actually this multivariate filtering method we have applied for schizophrenia detection using EEG signal. And the schizophrenia is a serious disease. It affects around 20 million people in the world, and that is actually 1% of the world population. And it has actually symptoms like hallucinations, and hearing, tasting, smelling, or feeling that does not really occur, disorganized speech, and thinking, abnormal motor behavior. So actually we have proposed this framework for schizophrenia detection using this multivariate filtering. So we have multi-channel data, then we perform segment test, take segments of 25 seconds, then we apply pre-processing, then we apply iterative filtering of multi-channel EEG data, then for each channel we determine the N modes, and then from that we determine the rhythms, delta, theta, alpha, beta, gamma rhythms, and then we extract features from these rhythms, and then we perform classification using machine learning based classifier, and which gives you the automated detection of healthy and schizophrenia EEG signals. So for that actually study, we have used publicly available database from Institute of Psychiatry and Neurology from Poland, and it has a database from 14 patients, and it also has 14 healthy signals, healthy subjects, and its sampling rate is 250 Hz, and duration actually is 15 minutes. So here actually you can see this MIMF multivariate filtering, this decomposition of EEG signals, the 3-channel EEG signal. And these are the actually second, third, and fourth IMFs. And in the frequency domain also you can see their spectrum. So these spectrums, they are actually aligned to each other. This means these modes are actually mode alignment properties preserved, and they have same, each channel, actually each component is representing the same frequency component for the different channels. And then we have actually, based on the mean frequency, we have separated these rhythms. So this is the delta, theta, alpha, beta, gamma rhythms for different channels, and based on the mean frequency lying in that particular range of the frequency of that particular rhythm, then actually that IMF is grouped to that particular rhythm. So in that way we have separated all possible rhythms, and that is actually delta, theta, alpha, beta, and gamma rhythms as separated. Then we extracted features, activities, earth mobility, and earth complexity. So then total number of features, that is 285, based on these rhythms we obtained, and this is actually a significant number of the features. It is very high. So we have actually ranked the features based on the probability value of the student t-test. So best 30 features have been selected among 285 features. So this table shows the most significant 10 features chosen based on the student t-test. And after this figure shows the actually box plot of the most significant 10 features. And that you can see from this box plots that these two classes, healthy and schizophrenia, nicely can be discriminated with these actual features. So these features are discriminative in nature. And then actually we have used machine learning based classifiers. So different classifiers are trained using best 30 features to differentiate EEG signals corresponding to healthy and schizophrenia classes. And this 30 features determined based on trial and error method, and then after 30 features we don't have a significant change actually in the classification accuracy. So based on that we have selected 30 features, and the following classifiers are used: support vector machine with cubic kernel, support vector machine with quadrature kernel, support vector machine with linear kernel, linear discriminant, k-nearest neighborhood classifier, decision tree classifiers. And then actually we have in order to measure the effectiveness of this classification system, we have evaluated accuracy, sensitivity, specificity, and positive predictive value parameters, and mathematical expressions of these performance measures can be seen in this slide. And here TP is the true positive and TN is true negative, and FP is false positive and FN is false negative. And then this table shows the actually performance measures of the different classifiers with best 30 features using 5-fold cross validation and 10-fold cross validation of the different classifiers. And accuracy, sensitivity, specificity, positive predictive value, area under ROC curve can be seen in this table. And this 10-fold actually provides better classification accuracy, better sensitivity, better specificity, better positive predictive value, and better area under ROC curve. And then we have compared our proposed method with other existing methods in the literature. And you can see the proposed method actually provide better classification performance in the automated classification of schizophrenia as compared to the other existing methods in the literature, which are studied in the same database. And this is the conclusion of this talk. Proposed multivariate empirical wavelet transform and multivariate filtering are able to decompose multi-channel and multivariate signal into meaningful components. And mode alignment is a most important properties of the multivariate decomposition technique. And proposed methods properly align the similar oscillatory components across the different channels. And the proposed techniques can have provided better detection performance for epileptic and schizophrenia diagnosis based on the scale PEG signals. So these proposed approaches can be useful in order to assist neurologists in their decision makings. And this computer smartphones with the proposed algorithms can be used for the diagnosis of these neurological disorders in rural areas where we have shortage of doctors. So this actually talk is based on these two of our recent publications. So in order to have more detailed information about this, whatever I presented, I request all of you please go through these publications. And thank you very much. Any questions, please?